Welcome to this coding walkthrough. Today, we'll be tackling a popular problem: sort colors from LeetCode. This problem involves efficiently sorting elements using specific constraints, and it's a fantastic exercise to practice algorithmic thinking. Let's dive in and explore various approaches to solve this step by step. In this problem, we are given an array called nums that contains objects colored red, white, or blue. These colors are represented by the integers 0, 1, and 2, respectively. The goal is to sort this array in place so that all objects of the same color are grouped together, with red, 0, coming first, followed by white, 1, and then blue, 2. Importantly, we are not allowed to use the library's built-in sort function, so we need to implement the sorting logic ourselves. The function modifies the input list directly and does not return anything. This means we need to focus on an efficient approach to rearrange the elements within the same array. Let's look at some examples to understand the behavior of the function more concretely. For the first example, the input array is 2, 0, 2, 1, 1, 0. Here, the integers represent the colors blue, red, blue, white, white, and red. After sorting in place, the output becomes 0, 0, 1, 1, 2, 2. This means all red objects are grouped at the beginning, followed by white, and then blue. In the second example, the input is 2, 0, 1. After sorting, the array is transformed into 0, 1, 2. Again, the colors are arranged in the order red, white, and blue. These examples emphasize that the sorting should not create a new array but instead rearrange the elements within the given array. In the third example, the input array is 0, which contains only one element representing red. Since the array is already sorted, no changes are needed, and the output remains 0. Similarly, in the fourth example, the input is 1, which contains a single element representing white. Again, the array is already sorted, so the output remains 1. These cases highlight that for single-element arrays, the function does not need to perform any operations, as they are inherently sorted according to the desired order. The constraints of the problem ensure that the length of the array, denoted as n, is between 1 and 300. Additionally, every element in the array is guaranteed to be either 0, 1, or 2, corresponding to the three colors. This means we do not need to handle invalid inputs. Some important edge cases to consider include single-element arrays, which are already sorted, and arrays that are entirely one color, such as 0, 0, 0, 1, 1, 1, or 2, 2, 2. These arrays also require no modifications. On the other hand, arrays with mixed colors, like 2, 1, 0, or 2, 2, 0, 1, need to be rearranged to meet the required order. Finally, it's worth noting that this problem is often referred to as the Dutch national flag problem. A common and efficient way to solve it is by using a two-pointer approach. This method allows us to sort the array in a single pass with a time complexity of O(n) and a space complexity of O(1). This means the solution is both time-efficient and space-efficient, making it well-suited for the given constraints, even for the maximum size of 300 elements. By leveraging this approach, we can ensure the array is sorted correctly while meeting all the problem requirements. To tackle the problem of sorting colors, let's begin by exploring some possible approaches. The most intuitive solution is the brute force approach, where we simply use a sorting algorithm like Python's built-in sort function. Since the integers 0, 1, and 2 directly correspond to the colors red, white, and blue in ascending order, sorting the array naturally places the elements in the desired order. However, the drawback here is that this approach operates in n log n time due to the sorting step. While it works correctly, it doesn't take advantage of the fact that our input only contains 3 unique values, and it doesn't meet the problem's requirement to solve it in linear n time. Now, a slightly better approach is counting sort. Here, we count the occurrences of each value 0, 1, and 2 in a single pass, and then overwrite the array by placing the appropriate number of zeros, followed by 1s, and then 2s. This method is efficient, running in n time and using O(1) space. It involves 2 simple steps: first, traverse the array to count the values, and second, rewrite the array based on those counts. While this is a significant improvement, it still requires 2 passes over the array, and there's an even better solution available. The Dutch national flag algorithm offers a more optimized one-pass solution. This method is ideal because it partitions the array into 3 distinct regions in a single traversal. The key insight here is to use 3 pointers: the low pointer, which tracks the boundary for zeros, the high pointer, which tracks the boundary for twos, and the current pointer, which traverses the array. As we process each element, we swap values as needed to ensure that elements before the low pointer are all zeros, elements after the high pointer are all twos, and elements between low and current are ones. This approach avoids the need for counting or additional passes, making it both time efficient and space efficient. By carefully managing these pointers, we can reorganize the array in a single traversal while keeping the algorithm simple and elegant. Let's break down the steps of the Dutch national flag algorithm. First, we initialize 3 pointers: low starts at the beginning of the array, high starts at the end, and current begins at the start as well. The traversal continues as long as current is less than or equal to high. When we encounter a 0 at the current pointer, we swap it with the value at low, then increment both low and current. If the value at current is 2, we swap it with the value at high, and then decrement high. Notice here that we do not increment current in this case because the new value swapped into the current position needs to be processed. Finally, if the value at current is 1, we simply increment current without making any swaps. This ensures all elements are placed in the correct order in a single pass. The result is an in-place sorting of the array with O(n) time complexity and O(1) space complexity. This streamlined approach avoids the need for additional passes or temporary storage, making it the most efficient solution. The key to understanding why the Dutch national flag algorithm is so effective lies in the insight that we don't need to perform a full traditional sort. Instead, by partitioning the array into 3 regions using the low, high, and current pointers, we can efficiently organize the elements in a single traversal. This insight is the true breakthrough moment for solving this problem optimally. When comparing the different approaches, the brute force method is the simplest but inefficient, with O(n) log n complexity, making it impractical for large inputs. The counting sort approach is an improvement, achieving O(n) time, but it still requires 2 passes over the array. In contrast, the Dutch national flag algorithm achieves the optimal balance with O(n) time complexity, O(1) space complexity, and only a single traversal. This makes it the most elegant, efficient, and problem-specific solution, perfectly aligned with the constraints and expectations of the task. To tackle the problem of sorting an array containing only the integers 0, 1, and 2, we'll use the Dutch national flag algorithm. This algorithm is both time and space efficient, operating in O(n) time complexity and O(1) space complexity. The key idea is to maintain 3 pointers: low, mid, and high. The low pointer is used to track the position for zeros, mid represents the current element under consideration, and high is used to track the position for twos. Initially, all 3 pointers are set as follows: low and mid start at index 0, and high is set to the last index of the array. This setup ensures that we can process the array in a single pass while keeping the placement of zeros, ones, and twos organized efficiently. As we iterate through the array, the mid pointer plays a crucial role in evaluating the current element. If the element at mid is 0, we swap it with the element at low, then increment both low and mid. This ensures that the 0 is moved to its correct position at the front of the array. If the element at mid is 1, no swapping is needed because 1 is already in its correct region, so we simply increment mid. However, if the element is 2, we swap it with the element at high and decrement high, moving the 2 to its correct position at the end of the array. Importantly, we do not increment mid in this case, as the element swapped from the high position still needs to be evaluated. The iteration continues until the mid pointer surpasses the high pointer, at which point all elements are sorted. This algorithm works efficiently because it processes the array in a single pass, leveraging the fact that there are only 3 distinct values. The low, mid, and high pointers divide the array into 3 regions during the sorting process. Specifically, the region before low contains only zeros, the region between low and mid contains only ones, and the region after high contains only twos. Additionally, this is an in-place algorithm, meaning it requires no extra space beyond the 3 pointer variables, which keeps the space complexity at O(1). Another advantage is that it naturally handles edge cases, such as empty arrays or arrays containing only one type of element, without requiring special conditions. Even arrays that are already sorted complete efficiently without unnecessary swaps. The primary data structure used in this algorithm is the input array itself, which is modified in place. The 3 pointers low, mid, and high are simple integer variables that help track the boundaries of the regions for zeros, ones, and twos. Two key operations drive the algorithm: swapping and pointer updates. Swapping is performed only when necessary, such as when moving zeros to the front or twos to the back, which reduces redundant operations and boosts efficiency. Meanwhile, updating the pointers ensures forward progress without revisiting already processed elements. Together, these operations enable the algorithm to complete the sorting task with minimal overhead. To understand how the algorithm works, let's walk through an example with the input array 2, 0, 2, 1, 1, 0. Initially, low and mid are set to 0, and high is set to 5. In the first iteration, the value at mid is 2. We swap it with the value at high, resulting in the array 0, 0, 2, 1, 1, 2, and decrement high to 4. On the second iteration, the value at mid is now 0. We swap it with the value at low, which keeps the array unchanged as 0, 0, 2, 1, 1, 2. We then increment both low and mid to 1. In the third iteration, mid is still pointing to a 0, so we swap it with the value at low again. The array remains 0, 0, 2, 1, 1, 2, and we increment low and mid to 2. In the fourth iteration, the value at mid is 2. We swap it with the value at high, resulting in the array 0, 0, 1, 1, 2, 2, and decrement high to 3. On the fifth iteration, the value at mid is 1, which is already in the correct region, so we simply increment mid to 3. Similarly, in the sixth iteration, the value at mid is still 1, so we increment mid to 4. At this point, the loop terminates because mid is greater than high. The final sorted array is 0, 0, 1, 1, 2, 2, demonstrating how the algorithm efficiently organizes the zeros, ones, and twos in a single pass. To solve the sort colors problem, LeetCode number 75, we use the Dutch national flag algorithm, which provides an efficient way to sort an array containing only 3 distinct values, 0, 1, and 2. This algorithm runs in O(n) time complexity and operates in place using 3 pointers, low, mid, and high. Explanation. 1. Initialization. We define 3 pointers. Low starts at the beginning of the array and represents the boundary for the sorted zeros. Mid starts at the beginning and is used to traverse the array. High starts at the end and represents the boundary for the sorted twos. 2. Traversing the array. While mid is less than or equal to high, we process the element at index mid. If the element is 0, we swap it with the element at low. This ensures that zeros are moved to the beginning of the array. We then increment both low and mid. If the element is 1, it is already in the correct position, so we simply increment mid. If the element is 2, we swap it with the element at high. This moves 2's to the end of the array. After the swap, we decrement high. 3. Edge cases. If the array is empty, the function does nothing. If the array contains only one type of element, e.g., all zeros, all ones, or all twos, the algorithm correctly handles this without unnecessary operations. This approach guarantees that the array is sorted in a single pass, making it both time efficient and space efficient. The key insight lies in how the 3 pointers dynamically adjust the boundaries for zeros, ones, and twos, ensuring that each element is processed exactly once. This is the Java implementation of LeetCode problem number 75, sort colors. The solution mirrors the logic from the Python implementation by using the Dutch national flag algorithm. The algorithm uses 3 pointers, low, mid, and high, to sort the array in a single pass, O(n) time complexity. Key differences include explicit type declarations for arrays and variables, and the use of Java's syntax for swapping elements. The code is concise and adheres to Java's conventions. Here, we're starting with the input array 2, 0, 2, 1, 1, 0, and the initial positions of our pointers are low equals 0, mid equals 0, and high equals 5. In the first iteration, the value at mid is 2. Since 2 belongs at the end of the array, we swap nums, mid, with nums, high, which moves the 2 to the last position. This updates the array to 0, 0, 2, 1, 1, 2, and we decrement high to 4. Notice that mid remains at 0 because we need to recheck the swapped value. In the second iteration, the value at mid is now 0, which belongs at the beginning of the array. We swap nums, mid, with nums, low. Since both values are already 0, there's no visible change in the array. After this, both low and mid are increment to 1, preparing for the next check. In the third iteration, nums, mid, is still 0, so we again swap nums, mid, with nums, low. Since both values are 0, the array remains 0, 0, 2, 1, 1, 2. Then, both low and mid are increment to 2. Next, in iteration 4, the value at mid is 2, which needs to be moved to the end. We swap nums, mid, with nums, high, updating the array to 0, 0, 1, 1, 2, 2. After this, high is decrement to 3, but mid stays at 2 to check the swapped value. In iteration 5, nums, mid, is 1, which is already in the correct position. Therefore, no swaps are needed, and we simply increment mid to 3. Similarly, in iteration 6, nums, mid, is again 1, so no swapping occurs, and mid is increment to 4, completing the process for this array. The final state of the array after processing is 0, 0, 1, 1, 2, 2, which is fully sorted. Now, let's look at a second example with the input array 2, 0, 1. At the start, the pointers are initialized as low equals 0, mid equals 0, and high equals 2. In the first iteration, the value at mid is 2, so we swap nums, mid, with nums, high. This moves the 2 to the end of the array, updating it to 1, 0, 2. After this, high is decrement to 1, and mid remains at 0 to check the swapped value. In the second iteration, the value at mid is now 1, which is already in the correct position. Therefore, no swaps are needed, and we simply increment mid to 1. Next, in the third iteration, nums, mid, is 0, which belongs at the beginning of the array. We swap nums, mid, with nums, low, resulting in the array 0, 1, 2. Both low and mid are increment to 1 and 2, respectively, completing the sorting process. The final sorted array for this example is 0, 1, 2. For the third example, we start with the input array 0, 1, 2, which is already sorted. The initial positions of the pointers are low equals 0, mid equals 0, and high equals 2. In the first iteration, nums, mid, is 0, so we swap it with nums, low. Since both values are already 0, the array remains unchanged as 0, 1, 2. Then, both low and mid are increment to 1. In the second iteration, the value at mid is 1, which is already in the correct position. No swaps are needed, so we increment mid to 2. In the third and final iteration, nums, mid, is 2, which is also in the correct position. Since no swapping is needed, we simply decrement high to 1. At this point, the pointers indicate that the sorting is complete, and the final state of the array is 0, 1, 2. These examples demonstrate how the algorithm handles different types of input arrays, whether they're unordered, partially sorted, or already sorted. By maintaining 3 pointers and making swaps only when necessary, the algorithm efficiently sorts the array in a single pass using constant space. The time complexity of this algorithm is O(n), where n is the length of the input array. This efficiency comes from the use of a single while loop that iterates through the array. The loop continues until the mid pointer surpasses the high pointer, ensuring that every element is processed exactly once. Depending on the value of nums, mid, the loop either increments mid, increments both low and mid, or decrements high. Each of these actions guarantees progress, either by moving mid forward or high backward. Since the operations performed within each iteration, such as swapping elements, take constant time, the overall time complexity is linear, or O(n). This ensures the algorithm is highly efficient in terms of processing time. The space complexity of the algorithm is O(1), as it operates directly on the input array without requiring additional data structures. This is achieved by sorting the array in place, meaning no extra memory is allocated for temporary arrays or intermediate results. The only additional variables used are low, mid, and high, whose count does not scale with the size of the input array. Since the memory usage remains constant regardless of the input size, the space complexity is considered optimal at O(1). The algorithm maintains a consistent time complexity of O(n) across all scenarios, including the best, average, and worst cases. In the best case, the input array is already sorted, such as 0, 0, 1, 1, 2, 2, but the algorithm still processes each element once. In the average case, where the array contains a random distribution of zeros, ones, and twos, the algorithm iterates through all n elements, maintaining its linear time complexity. Even in the worst case, such as when the array is completely reversed, for example, 2, 2, 1, 1, 0, 0, the algorithm processes each element exactly once. This consistency highlights the robust efficiency of the approach. When compared to naive approaches, the given algorithm is clearly more optimal. A naive method might involve sorting the array directly using a comparison-based algorithm like quicksort or mergesort, which would result in a time complexity of O(n) log n. Mergesort, for example, would also require O(n) space, while quicksort would need O log n space. Another alternative might involve counting the occurrences of zeros, ones, and twos in a first pass, and then reconstructing the array in a second pass. While this method achieves O(n) time complexity, it still requires two separate passes, whereas the given algorithm processes the array in a single pass. Additionally, the algorithm uses constant space, making it optimal in both time and space complexity. To mathematically prove the O(n) time complexity, consider that the length of the array is n. The while loop ensures that either the mid-pointer is increment or the high pointer is decrement in each iteration. Each iteration processes one element by either swapping or moving pointers, which guarantees that the total number of iterations does not exceed n. As a result, the time complexity is O(n). For the O(1) space complexity, note that the algorithm does not use any auxiliary data structures or allocate memory proportional to the size of the input. The memory usage is limited to a fixed number of pointers, such as low, mid, and high, which remain constant regardless of the input size. Therefore, the algorithm is both time and space efficient, achieving optimal complexity for this problem. When tackling the sort colors problem, there are a few common mistakes you need to watch out for. First, ignoring edge cases can lead to unexpected errors. For instance, what happens if the input is an empty array, or contains just one element, or all the elements are the same? These scenarios must be explicitly handled in your code to ensure it behaves correctly. Another mistake is assuming the input size will always be small. If your solution doesn't account for large inputs, like arrays with tens or hundreds of thousands of elements, you might run into performance issues. Always evaluate the time and space complexity of your approach to ensure it scales well for such cases. Additionally, misunderstanding the problem requirements is a frequent pitfall. Make sure you carefully read the constraints, such as whether the array is already sorted, if duplicates are allowed, or if the solution must be in place. Finally, overcomplicating the solution can waste valuable time. It's often better to start with a simple, clear approach and refine it incrementally, rather than jumping straight to complex algorithms or data structures unnecessarily. Another mistake is failing to optimize for space when required. Some problems, including sort colors, may ask for an O(1) space solution. If you use extra memory unnecessarily, such as creating a copy of the array, you could fail test cases or exceed memory limits. Now, let's talk about some important interview insights. Sorting problems, like this one, often serve as the foundation for follow-up questions involving binary search or two-pointer techniques. These patterns are incredibly common in coding interviews and worth practicing. Similarly, if the problem involves searching for a specific sum, difference, or condition, hash maps or sets can be highly effective for O(1) lookups, which is much faster than nested loops. During your interview, make sure to clarify the exact requirements. For example, ask whether the input is already sorted or if sorting is necessary. Misunderstanding this detail could lead to redundant computations. Lastly, manage your time wisely. If you're unsure of the best solution, start with a brute force approach to demonstrate correctness, then work on optimizing it. Remember, explaining your thought process clearly is often more valuable than jumping straight to the most optimal solution. When preparing for interviews, make it a habit to ask about edge cases. For example, you might ask, how should the function handle an empty array? This demonstrates that you're thorough and attentive to details, which interviewers appreciate. Now, let's briefly discuss related problems that share similar concepts with sort colors. Problems like LeetCode 1, 2-sum, and LeetCode 15, 3-sum, also involve array manipulation and often require techniques like sorting, two-pointers, or hash maps. Similarly, LeetCode 16, 3-sum closest, and LeetCode 18, for sum, build on these ideas, adding layers of complexity. Practicing these problems can help you recognize patterns and refine your ability to apply the right techniques efficiently. Finally, let's explore some alternative approaches you might encounter. One common method is to sort the array first and then use two pointers. This approach is effective for problems involving pairs or triplets that meet a certain condition, as it reduces the time complexity to O, n log n, for sorting and O, n, for processing. However, this assumes the input can be sorted, which isn't always possible. Another alternative is to use a hash map or set for quick lookups. This is particularly useful for problems like 2-sum, where you need to check if a complement exists in constant time. The trade-off, of course, is an increase in space complexity to O, n. Lastly, divide and conquer techniques can be applied to problems that involve finding maximum or minimum values in subarrays. These approaches can reduce complexity compared to brute force but are often more complex to implement and may require a deeper understanding of recursion. Each of these methods has its strengths and trade-offs, so it's important to choose the one that's best suited to the specific problem constraints and requirements. Great job! Today we explored solving the sort colors problem efficiently, focusing on in-place sorting and single-pass algorithms. Remember, knowing when and how to optimize algorithms is key in interviews and real-world applications. If you enjoyed this session, don't forget to like, share, and subscribe. Happy coding, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!